So, the motivation of this lecture is to give you the philosophy with which one designs a catalyst. Okay, so what is the basis for computational catalyst design? When I say catalyst, I'm referring to heterogeneous catalyst, homogeneous catalyst, and electrocatalyst. And there are attempts to extrapolate these methods to, let's say, biocatalysts also. And in principle, this is applicable to a wide variety of systems, but you are often limited by the computational time. The larger systems they are harder to compute. So you have to choose the system judiciously. Okay, so that's what we will that's what you should try to understand at this point of time. So, so what do I mean by long ago, far away? Okay, so the underlying, so this is a very much celebrated quotation by Paul Dirac in 1929. He was one of the pioneers in quantum mechanics. So let's read through, I'll just read the quotation. The underlying physical laws necessary of a large part of physics and the whole of chemistry are thus completely known. So what were the physical laws he was referring to? These are the laws of quantum mechanics. So much of physics has to do with laws of quantum mechanics, maybe statistical mechanics also, and electrodynamics and mechanics. These are the various branches, but quantum mechanics plays maybe 80% of physics rely on the laws of quantum mechanics. And almost all of chemistry, when we are talking about chemistry or chemical engineering systems, catalytic systems and chemical engineering, we are thinking about bond breaking. All right, so bonds are formed or bonds are broken. And this, what governs, what are the rules that are relevant for bond formation and bond breaking? Dirac's opinion was that they originate from quantum mechanics, all right? So the laws are completely known. Okay, so that's great, right? So a chemical engineer are typically, they are all interested in design, okay? Can you put all these fundamental laws to some practical utility, all right? So there was a chemical engineer in 1929 who said, oh, okay, if the laws are completely known, I can use these laws to design a catalyst ab initio. What do we mean by that? This particular word, ab initio, means from first principle, okay? Instead of an empirical approach of synthesizing a catalyst and making and testing its reactivity, can I use these fundamental laws, quantum mechanical laws, to design a catalyst from first principle? That was the goal. And there was this chemical engineer, she asked this physicist, she was very excited, and then asked this, okay? And there was another chemist, okay, he said the following: I can solve Schrodinger equation. Okay, this is the most fundamental equation in quantum mechanics. For hydrogen atom, exactly. That means the analytical solution, okay, for Schrodinger equation for hydrogen atom is possible. However, with helium atom, with lot of analytic and manipulation, maybe with some difficulty, and I can do that. Maybe numerical approaches are also possible. So, I mean, this complexity, the chemical complexity of this system is far less compared to a real catalyst, right? So a real catalyst has a complex, it's a particle, a real heterogeneous catalyst has many components. It has a very complicated structure. It has a microstructure and so on. So compared to the structure of a real heterogeneous catalyst, these are far less simple. Okay, so if the logic here is, if even for such simple system there's a lot of difficulty, so the chemist, he told this chemical engineer, that forget heterogeneous catalyst. Okay. So, and she was very disappointed. This chemical engineer in 1929, she told him that forget quantum mechanics. Okay. So that's what happened to quantum mechanics and chemical engineering. There was not revisited. But over the last 2 decades, slightly over 2 decades, things have really changed. Chemical engineer has become a quantum mechanic. You know, the mechanic is someone who engineers, gets things done, right? So what are we seeing here? So what I was trying to illustrate is nowadays engineers, how do they rationally design materials, catalysts in this case. So this, let's say an FCC reactor, this is what you are interested in, doing something at a large scale, producing something of a certain value, economic value. So what they try to do is they engineer a wave function. Okay, so this is a central object of quantum mechanics. Let's say we refer to this wave function with this symbol, psi of r. And if you can engineer the wave function for a particular heterogeneous catalyst, that gives you a way to design a heterogeneous catalyst in a rational manner, in a structured manner, okay, without resorting to a lot of empiricism. Okay, so it was well demonstrated by a lot of work that was done by Norsko and his group. First, he was there in DTU, Danish Technical University, and then he moved, spent about 10 years in Stanford Chemical Engineering department, and he's back in DTU, I suppose. So one of the example which was well demonstrated, okay, very well demonstrated, was ammonia synthesis catalyst. Okay, so ammonia synthesis plays an important role in the development of chemical engineering, right? So in the early 1900s, 1920s and so on, ammonia, so what was the context? We wanted to take nitrogen from the atmosphere and so on. So you want to make ammonia which can be used for fertilizers, right? Because this is a big problem. This is a very, very important problem. Chemical engineers use lots of knowledge available in applied chemistry, chemistry and applied chemistry, and demonstrated ammonia synthesis in a grand scale. Because it was a great success story of chemical engineering. So that was done mostly via experiments. Okay, certain lots of combinatorial experiments were attempted to discover what is a productive, efficient ammonia synthesis catalyst. So as opposed to what was done at that time, 80 years later, here people have demonstrated, Norsko and his group have demonstrated how to use computational quantum mechanics to discover new ammonia synthesis catalysts. So what are we plotting here? So this is an empirical quantity on the y-axis. It's called turnover frequency. It is a measure of activity of an ammonia synthesis catalyst. On the x-axis, what we are plotting is some kind of a binding energy, or let's say nitrogen binding energy, to the surface, okay, to the various surfaces involved. Okay, so what is the goal here? So let's say you have a traditional ammonia synthesis catalyst. Let's say it is made up of ruthenium, osmium. These are all very expensive materials, right? So supposing I don't want to use these expensive materials for ammonia as an ammonia synthesis catalyst. I want to replace this expensive material with some other less expensive material. So that was the goal here. So what we are plotting is, let's say we are plotting the rate of ammonia synthesis as a function of different, supposing you're doing ammonia synthesis in different catalysts, all right? Supposing I'm trying to do ammonia synthesis on molybdenum catalyst. That's not a good catalyst. The activity is very low. Likewise, the activity of ammonia synthesis on nickel catalyst is very less, all right? So they have, both these materials, molybdenum and nickel, both have very less reactivity for ammonia, so ammonia synthesis. However, the reason for why they are less reactive is very different. Okay, so this is all based on what we call Sabatier principle. So the reason why molybdenum is a bit bad catalyst is different from why nickel is a bad catalyst. Let's say then you move on to iron and cobalt. They are not as bad as nickel and molybdenum, but they're slightly better, but still they are not as active as the most active ammonia synthesis catalysts. All right, ruthenium and osmium, they are, let's say, the most active ammonia synthesis catalysts. But what we find is again, so this is called a volcano plot, okay, because this looks like a volcano, right? So this structure looks like a volcano. So so what you say, this is one leg of a volcano, right? This is another leg of a volcano. So the general principle here is you take a material which is on this leg of a volcano and combine with another element, okay, which is in this leg of a volcano. Combine these two materials here, molybdenum and cobalt, and you form an alloy. All right, you form a bimetallic alloy. And what is found is, very interestingly, when you combine two different materials which are not that reactive, you get a material, new alloy, which is very active. All right, so that is the significance here. Okay, this was a dramatic thing. And see, what we have to understand is this is a quantity which is obtained from computational quantum mechanics. This is more or less binding of, let's say, nitrogen on different materials. Okay, and on the y-axis you have activity. All right, this is an experimentally experimentally measured quantity. You can also compute it. Okay, but the comparison here, like what is predicted, and when you're comparing it with the experiment, the comparison is very good. So the general take-home message here is, you take a material, an element from a metal from one leg of a volcano, combine it with another element from another leg of a volcano. Both are individually not good catalysts. When the combined system is a very active heterogeneous catalyst. Okay, so this is Sabatier, if I remember right. He developed these principles in early 1900s, 1908 or something like that. I think it's 1908. All right. So these conceptual principles were around. All right. So how do you make it more applicable for a variety of materials? I mean, in the sense that, how do I calculate the binding energy for a variety of materials? That computational structure based on quantum mechanics was not available till close to 2000. This was done in 1998 for the first time, right? Because large computers were not available when quantum mechanics came alive. Okay, so the quantum mechanics, much of the laws were formulated in 1920s and so on. Some of the principles of catalysis, Sabatier, Paul Sabatier, he framed these things in early 1900s. Okay, so but what changed? The technology changed. Okay, so big computers were widely available close to 2000. Okay, so the technology changed, even though the conceptual framework were around even before that. Okay, so that is a rational design of catalysts. So the less of empiricism and so on. Okay, so here again, just to summarize what is there in this schematic, is on the y-axis we are plotting turnover frequency. This is a measure of reactivity of a heterogeneous catalyst for ammonia synthesis. On the x-axis, I have adsorption energy, right? Binding energy of nitrogen for various transition metal and transition metal alloys, right? Okay, so the predicted alloys, okay, so the reactivity on the predicted alloys compared very well with measured reactivity. So that's the important thing. Finally, you may compute this and that. Okay, so very important thing is you have to eventually look at experiments. Okay, so the judgment is going to be judgment of the power of your model is going to be made by experiments. All right, but even when you do that, you should know at what level you want to be compared. Right, so you're not going to compare at the level of binding energy. Okay, the binding energy computed computationally and measured against experiment. That is a useful comparison, but that's not the most relevant comparison here. Here, let's say there's a computational approach to compute binding energy, and using that, you have built a rate model for ammonia synthesis, and then you have measured some, you computed some rates, all right, and you're comparing the computed rates with experimentally obtained rates. If that comparison is very good, then you are really, it's a very successful paradigm for thinking about a catalyst design, right? So this is a review paper, it's a useful review paper. So you should try to read that, okay? So, or we'll come up with small review papers that is more accessible for the class. So all this, how did computation, so the next thing you have to understand is how did computational quantum mechanics become a practical engineering tool? That depends upon this many-body quantum mechanical theory called density functional theory. Okay, so I'll elaborate. Okay, so this is the rest of the class. We're going to slowly elaborate these things. So what we mean by density of what? We're talking about electronic density. What? Why is this a typo? This is not a typo. This I'm talking. This is not a function. This functional. So we'll define what's a functional. Function is a one-to-one map. This is functional is a many-to-one map. We will define all these things as we go along in this class. So this is a theory which is very good for obtaining energies. All right. So this is for energies of obtaining variety of chemical process. In this case, in the case of a heterogeneous catalyst, this is a theory which is very relevant for obtaining the energies of surface chemical processes. For example, what am I referring to here? Let's say you are interested in binding energy of nitrogen on a variety of materials. Okay, so in the previous slide, we were talking about reactivity in binding energy in cobalt, binding energy in molybdenum, and so on. So density functional theory is a good theory for giving energies of surface chemical processes at a relatively less computational cost. Okay, so this is accessible to computers from available in let's say late 1990s and so on. So DFT, density functional theory, is not a good theory for obtaining absolute binding energies. Let's understand what we are trying to say. So if I am interested in obtaining the binding energy of nitrogen on a particular metal, let's say molybdenum, DFT, and then I compare it with experiments, DFT might not do a good job. Okay. However, so then you may ask, okay, so isn't that theory very deficient? Why am I using that theory at all? Okay, so you may ask that question. It's a valid question. So let's understand what is the power of DFT. However, DFT gives good trends in energy. Supposing I'm in the previous slide, I saw there were some 6 elements, and I'm interested in trends in binding energies in 6 elements. Okay, so DFT will tell you which of these elements bind very well, which bind very weakly to nitrogen. Okay, so the general framework here is trends in energy will help in catalyst design. Okay, so that was the idea with which people approached computational catalyst design from using density functional theory. Even though we don't have, even though DFT is not very good for obtaining correct absolute binding energies, it does give correct trends in energies, and using these trends in energy, we are trying to design catalysts. So just a summary slide. Okay, so we are going to elaborate all these one slide in many lectures. Okay, as we progress. So just to summarize, what made density functional theory a practical computational scheme? So the central object, as I mentioned in quantum mechanics, is the Schrodinger equation. It's the wave function, which is obtained as a solution to Schrodinger equation. All right. So for an n electron system, it has 3 n dimensions. Okay. So each electron, psi, let's say you have a wave function for a particular electron. It's a function of x, y, z. Okay. And so if you have n electron system, it's the many body wave function has 3 n dimension. The computational cost goes as 3n to the power of gamma. Gamma can, depending upon the nature of the theory, can be between 2 to 7. Okay, so there are lots of theories in approximate theories. Okay, you make Schrodinger equation, you know the correct equation, you make lots of approximation, okay, perturbative methods and coupled cluster and so on. You have all these methods in quantum mechanics. So they scale in this manner. Okay, so this is not very practical. Okay, so as soon as the number of electrons increase in your system, your computational cost is scaling very badly. Okay, this is not very productive. Okay, so this is not really this is not going to help us, for example, in a problem like computational catalyst design. So there was always attempts to replace, instead of actually computing wave function, can we use scalar density? All right, instead of so what is I'm talking about the electronic density. That's a scalar quantity. So can I obtain energies using this electronic density? So this was explored from the early days of quantum mechanics by Fermi and so on, Thomas Fermi model and so on. There are things we will look at it as we progress in this class. So the main thing is this is if you can do this, the computational cost is much lesser, right? So the scalar density, all right, so irrespective of the number of electrons in a system, the scalar density has lesser dimensions. Okay, that's the important thing to note. So even though there was, from the early let's say 1920s, 30s and so on, this was being explored, but whether it is exactly possible, that was not known. So what really changed was a theorem by Walter Kohn and Hornberg in 1964, where they said that energy is a unique functional. Okay, so see, this is a function. Okay, for every r there is a particular row. That's a one-to-one map. Okay, this is a symbol you use for function. So we'll define what's a functional. Whether energy is a unique functional of electronic density, that was proved. It's a very simple proof. Was demonstrated by Walter Kohn and Hornberg in 1964. This is put the theory in firm footing, right? So, and then, even though this theorem was possible, I mean, this was demonstrated, a practical computational scheme came very soon. Okay, so Walter Kohn worked with his postdoc Sham. Okay, and then they came up with a computation scheme, a practical computation scheme. It's called the Kohn-Sham approximation, which which translated this theorem into a practical computational scheme, right? So using Kohn-Sham orbitals. So what do we mean whenever we are talking about orbitals? Orbitals are one electron wave functions, all right? So using what is called Kohn-Sham orbitals, you can compute the kinetic energy of the electrons, construct the density, the density, electronic density using Kohn-Sham orbitals. And then there is another thing called exchange and correlation. There are various approximations were used. All these things helped in obtaining energies as a functional given the electronic density, you are able to get energies. Okay, so this all may look rather heavy because we have tried to summarize. Let's say there are one semester courses in density functional theory. We have tried to summarize all these things into one slide, okay, in a very broad brush hand-waving manner. But we'll elaborate this later in the class using a few more lectures along the way. Okay, so just to give you a gist of what's going on here. So how okay, so this is a computational quantum mechanical framework which we are going to use. We'll elaborate rather later in the class. So what is the framework in terms of catalyst design? So this was very well practiced by Norsko's group. All right, he worked with lots of his students, all right, and grad students, approach this for a variety of important problems. It's very important to see there was in a way, threefold convergence. There was a large computation group working with a large experimental group, and they were in close contact with a leading company called Topsy, okay, who were a very big player in ammonia synthesis. So it's very important. So you should first know the contact with industry tells you what is an important problem that needs to be solved, okay, which is of commercial consequence. And then you have to first know that, okay, what is the problem that needs to be solved. And then you should also know if you're computing something, there should be a close comparison with experiments. Okay, so as I mentioned in some of the earlier lecture, you should know at what level you can make a comparison. What is being measured? Can I compute what is being measured? Okay, that is a maturity we should try to develop. So they demonstrated computational catalyst design framework for a variety of important chemical engineering problems: ammonia synthesis, fuel cell synthesis, methanation. All right. So we will see, we will see as we go along, do case studies of these things. So as I just mentioned, there was a strong experimental group with whom you can compare what was computed against experiment. And this industry also played an important role. Topsy played an important role in this whole framework. Okay. So there's an important thing here. Okay. So if you look at all these examples, okay, so you first identify what is the crucial bond breaking step. Okay, so in chemical engineering, we have notions of rate determining step. Right, so we have this notion of rate determining step. You first identify what is the tentative bond breaking step in all these processes. Okay, for example, ammonia synthesis, you know that there are two reactants involved, nitrogen and hydrogen. Between these two, we know from high school chemistry that nitrogen is a more difficult bond to break. All right, in fuel cell, the reaction is between, let's say, the reactants involved are O2 and H2. Okay, so that is the O2 is the more difficult reactant to break. Okay, so you identify what is the rate determining step, and you optimize. Okay, you compute the energetics of bond dissociation using bimetallic alloys. Okay, so in the 2 slides ago, I showed that you formed an alloy between cobalt and molybdenum. Okay, this is a alloy formed between two metals. Okay, so you optimize the bond breaking step across bimetallic alloys. So it's very important. Okay, so it's very interesting, all these things. Or in a way, this is a reductive system. Okay, so when you start with the metal, it is quite possible that the metal may get oxidized and form a metal oxide under the reaction condition relevant to catalysis, right? So that's quite possible, okay? So let's say, but in an ammonia synthesis condition, it's a reductive atmosphere. So what you try to, so the metal remains a metal, okay? And then there's an advantage with dealing with metals compared to oxides or nitrides or sulfides, in the sense that the structure of metals is relatively simple. Okay, so you might have heard in your previous classes that is so the metals FCC and HCP structures form a close packed structure. Okay, so this is a close packed structure in 2 dimensions. If you see, so if this is a close packed structure, we'll elaborate again this in later in some classes. So at least the take home message here is the structure of this metal is and the metal and metallic alloys is relatively simple. Okay, so this is an input for your quantum mechanical calculation. Okay, so unless you know the structure, you are not going to get the energies right. Okay, if there is a lot of uncertainty in structure, it's going to be hard for you to get any reasonable energies out of that. Okay, so because you started with metals as opposed to oxides or sulfides and nitrides, the structure is relatively simple. So, and then the other things which I talked about in the previous 2 slides before, this thing called exchange and correlation. We'll clarify this. Okay, these are fundamental notions that come about because electrons are fermions. We'll clarify all these things. They have exchange interaction and they have correlation interactions. Okay, this is because electrons are fermions as opposed to, let's say, photons, which are bosons. Okay, we'll clarify these things at a later stage. So this exchange and correlation energies can be more easily computed for metals. Okay, they can be approximated as a homogeneous electron gas. Right now, all these things are jargons, but along the way, after some preliminary quantum mechanics, we will clarify all these things. So this is just more like an introductory lecture. So I'm just giving you a big picture here, right? So what are the things? Just to summarize here, first, this must be a close comparison between what is computed and what is relevant experimentally. And then you optimize the bond breaking step over a range of bimetallic alloys. And these are metallic alloys. The structure is simple and computations are also relatively simple. And so just to summarize here, okay? So what is the introductory assertions, okay, for a computation catalyst design? If you know the surface structure of heterogeneous catalysts or even electrocatalysts, if you know that with reasonable certainty, okay, if it's reasonably correct, density functional simulations can give reasonable trends in reactivity. Okay, so that's what we are looking for, right? So once you have a reasonable trends in reactivity, which is more reactive, which is less reactive, you have a catalyst right then and there. All right. So this is an important assertion. Okay. If you know the structure, atomic structure reasonably well, you can get good trends in reactivity. In principle, this is valid for a variety of reaction, but practically it is implemented for only, with time, the complexity of reactions has increased. Okay, in the late 1990s and early 2000s, people were looking for diatomic molecules. All right, so the important bond breaking step in amino synthesis N2 for fuel cell catalyst is O2. Methanation catalyst also we will see what is an important step there. Okay, for methanation. Okay, so people focused on diatomic molecules. Okay, and then first they tried to see whether it's implementable for simpler systems before going to more complex systems. Okay, so the frontier has moved from early 2000s to now we're into 2020. So it has moved. All right. So to do this, the one more thing is if we want to go from energetics to kinetics. Okay, we want to get a measure of rate, which is the thing with which you want to compare with experiments. Okay, rate information. All right. So complete elucidation, okay, of kinetics is at first possible for many systems. Okay, so we will clarify this gradually as we go along. So to think about rates, okay, kinetics, chemical kinetics, it is very important to have some idea of what is the rate determining step. Okay, so in chemical engineering, you have learned that rate determining step is a particularly difficult step along as the reaction proceeds. That is the major determinant of the rates. Okay, we have this notion. To go from that, so we are going to clarify something more on that. Okay, so we have this notion of what is the transition state. Okay, so this is a picture you might have seen from high school. So we have whatever I plotting here. this is something called the reaction coordinate. Okay, as the reaction proceeds, okay, from the reactants you go to a product. On the y-axis, I'm plotting some measures of energy. It can be internal energy, it can be enthalpy, it can be free energy. Okay, we'll see where each of this is applicable. There is a potential energy surface. Okay, as the reaction goes from the reactants to the products. Okay, so we are typically taught that there are some steps. This has a lesser activation energy. What do I mean by activation energy? So the difference between this step and this step. Okay, this is the activation energy. So there are 3 activation energies here. Okay, this one, and this one. This has very less activation energy, and this has this has the most activation energy. All right. So you typically have this notion that the rate is controlled by this particular step. Okay. So actually, this is a 2-dimensional representation. This is actually can be misleading. All right. So you can plot this potential energy surface in 3 dimensions. Okay. So instead of one reaction coordinate, you can have a much more complicated reaction coordinate. So what do I mean by reaction coordinate here? Okay. So for example, let's say ammonia synthesis catalyst. Okay. The reaction coordinate can be the distance between hydrogen, center of mass of hydrogen, and the center of mass of nitrogen. That can be one measure of energy of the system. Okay, and then it can be the bond length of nitrogen. That can be another reaction coordinate. The bond length of hydrogen can be another reaction coordinate. Okay, so you will clarify this again. Okay, this is just an introductory lecture on this. So I can compute energy as a function of variety of reaction coordinates. So in this case, let's say I have 2 reaction coordinate. So actually transition state is a saddle point. Okay, so what do I mean by saddle point? It is a minimum along one direction, but a maxima in orthogonal direction. All right. So if I look at, if I plot the energy, and if I look at the energy as a function of in this direction, okay, as a function of this coordinate, I have a minimum. But if I look at the energy as a function of this coordinate, I have a maximum. Okay, so what is the transition state? Transition state is a saddle point. Okay, so here this looks like transition state is a maxima. That is not really accurate. So if I look, if I plot the energies in a multi-dimensional system, multi-dimensional reaction coordinate. Okay, transition state is a saddle point. Okay. All right. Okay. So we'll think about this. We will use this concept very later in the class. Okay. So typically transition states are harder to compute and harder to measure. Okay. Couple of Nobel Prize, okay, has been given in for measuring properties of transition states. Okay. So transition states are if you look at there's an important 2 things you have to know. Okay, one is 2 structures. Okay, when you think about reactivity, these structures here are called reaction intermediates. Reaction intermediates are structures which correspond to local minima. All right, so they have some lifetime. Okay, so when the system is at this point, okay, they can be isolated. Okay, or isolated at least for some time. All right, before they may still convert to some other quantity, some other chemical entity, but they can still be isolated for some time. They have a finite lifetime. But these transition states are very, very short-lived intermediates. All right, so it is very, very hard to experimentally capture the properties of transition states. A lot of very advanced spectroscopy was done by Ahmad Zewail, and who obtained the Nobel Prize for thinking about these things, called femtosecond spectroscopy, was done to understand the properties of transition state. So, the take-home message here is you have to differentiate the transition states are different from reaction intermediates. reaction intermediates are a minima in all reaction coordinates. Okay, but however, a transition state is minima along, in this case, a minima along one reaction coordinate. However, it's a maxima along other reaction coordinate which is orthogonal to this coordinate, right? So this is harder to not only measure, it's harder to compute also. How to exactly locate the transition state, it's a hard, challenging computation problem. So, however, there are certain features of this problem that has made this whole thing amenable to analysis, all right? Amenable to theoretical design. So, can features of transition states which are harder to measure, harder to compute, can that be correlated to something easier to compute? Okay, so that was something that was explored. Okay, so typically the important thing to understand here is activation energy. These are harder to compute, but they can be correlated to something easier to compute, absorption energies. Okay, so this is an important practical breakthrough. Okay, so this again was not something that was demonstrated, that was discovered in early 2000 or late 1900s. Okay, these things were important breakthrough in chemical kinetics, was done by Polanyi, Bronsted, and okay, again resulted in Nobel Prize. Okay, these are all important advances in chemical kinetics. Okay, that existed. This knowledge existed, and it was demonstrated using some experiments. Okay, but this strategy, okay, was adopted for computational catalyst design. All right, so we will stop here, and we will elaborate this on in the next few more later.